Hello, this video presentation shows an example of two-factor analysis of variance in which blocking is included as the second factor. So why do we block in an ANOVA? And as I write here, it allows us to further reduce the level of unexplained variation, which we call error in an ANOVA, by explaining a portion of that unexplained variation with a second factor. Now consider the crop yield example which I used in the previous video presentation. What we've done here is to recognize the type of farmland right here as an additional factor that might explain crop yield. And this is because we believe that the location where the crops are planted may also have an impact on crop yield. We hypothesize that the different locations where the crops are planted might have different soil texture, different climatic conditions, and that there may even be differences in the gradients of the land and overall topography, if you like, all of which might have an impact on the quality as well as on the quantity of crop yield. Those of you who are familiar with crops such as coffee and grapes know how these natural characteristics can impact the quality of coffee and the fine wine that you enjoy. Alright, here on this table, in addition to recognizing variation in crop yield right down here due to differences in fertilizer type, there are 3 of them up there. We also recognize differences in crop yield right here on the side due to differences in farmland. There are 5 of them right here. So notice that if we were to proceed and calculate the sources of variation so as to summarize our analysis of variance, we're going to use the same model to calculate sum of squares treatments, and also sum of squares blocking and sum of squares total. For treatment, it's always going to be the square difference between each treatment mean and the grand mean, and we're going to multiply by the number of observations in each group. If I go back here, you're going to see that there are three levels right here, and each has 5 observations. And for blocking, it's going to be the same thing. We're going to take the mean for each block, and there are, if I go back here, 5 of them, A, B, C, D, and E, and for each parcel of land we have 3 observations. Alright, and so this n sub j here is going to be 3, and then this is going to be the square difference between the grand mean and the mean for each of the 5 blocks. And for sum of squares total, it's always going to be the square difference between each observation and the grand mean. When you do all of those, you're going to get these results that you see here. Sum of squares error is better calculated by simply taking the sum of squares total, in this example 328, and then subtracting the sum of squares treatment and sum of squares blocking to get 28.8. And with all of those, you summarize in this on this ANOVA table for treatment and for blocking. Now, degrees of freedom for treatment is always going to be the number of columns minus 1, which is the number of levels of treatment, 3 minus 1. For blocking, there are 5 of them, so 5 minus 1 is 4. So I use notations easy to understand. C refers to the number of columns. If I go here, there's 3 columns. And B is the number of blocks, and there's 5 of them. So going right back here, for total degrees of freedom, it's always going to be n minus 1. So that gives you 14 because there are 15 observations in all. Minus 1 is 14. For the degrees of freedom associated with error, which is 8, one of 2 ways to deal with it. Either you do it by deduction, which is 14 total degrees of freedom minus degrees of freedom associated with treatment, and which is 2, and the degrees of freedom associated with blocking, which is 4. So that gives you 8. Or simply multiply the degrees of freedom for treatment by that for blocking, alright, which is what I show here. 2 times 4 gives you 8. And as usual, you're going to find the calculated F value by dividing each mean square by the mean square error. So the mean square treatment of 68.6, which comes by dividing sum of squares treatment by its degrees of freedom, you divide it by 3.6, which is mean square error. Ditto for blocking. And these are their calculated F's, which you can then compare to the critical value. So now here's an interesting summary which I showed you right here. Notice that if we had tested this model without blocking, as in this first table I show you right here, if we had tested it at the 5% level of significance, we would have initially rejected the null hypothesis, because as you can see here, this p-value is less than 5%. But in this study, though, we tested at the more conservative 1% level of significance, and as a result, we weren't able to reject the null hypothesis. As you can see right here, our p-value of about 3.87% is greater than alpha of 1%. Now we introduce blocking, and this is the results which I showed you already using manual calculation right here. So this is quickly summarized right here. So with blocking in place at the same 1% level of significance, notice that we are now able to reject the null hypothesis, because as you can see, the critical value for treatment is now greater than the calculated value, F value, is now greater than the critical value. Alternatively, notice that the p-value for treatment is less than the level of significance of 1%. So what this means is that by controlling for the differential impact of type of farmland, we were able to explain more of why there are differences in crop yield due to fertilizer type. Initially it didn't come out significant, now it comes out to be significant. And by that, we're able to further reduce the previously unexplained variation, which, as you can see, measure of unexplained variation, which is right here, looking at mean square treatment, drops from 15.9 without blocking to 3.6 with blocking. For this reason, this F statistic of 19.06, which is calculated as the ratio of the mean square treatment of 68.6, the same as it was without blocking, and the mean square error, which is now much smaller, comes out to be a much larger number than it was previously. So as you can see, definitely blocking has done its magic, because by controlling for variation in the types of farmland, we're able to more definitively determine that indeed differences in fertilizer type, which is the main treatment here, do actually impact the crop yield that you achieve. So these are quickly summarized right here for the main treatment variation, which is types of fertilizer. As you can see, the calculated F exceeds the critical value, as well as for blocking, where also the calculated F exceeds the critical value. And this wraps up this presentation.